Number 30, Dog Food Inc. wishes to design a can of volume 100 centimeters cubed using the least amount of metal as possible. Okay, so least amount is important. The can has to be cylindrical with a lid and a bottom, so that is important too. There's a top and a bottom, and it says find the dimensions it should use. So this is going to be an optimization problem. Okay, and so you can kind of usually tell because least amount, remember, means absolute minimum. So in all optimization problems, we are finding absolute extrema. So we're either going to maximize something, minimize something. We don't always have to use the word maximum and minimum. We don't have to use the word absolute, because by the definition of optimization, it is the absolute extrema. Look for synonyms, so you'll see words like least, smallest, right, to allude to that. So one of the things that we've done in recent years, and you'll see, is that these problems tend to be what we call scaffolded out, meaning they break them up into parts to help you guide you a little bit. So if you look at some of the older final exams, you might see an optimization setup and then a big empty sheet of paper. So the parts do tend to help sort of guide you through what you need to do to kind of help you through the problem. So let's look at this. So part A says, sketch the can, label the height h and radius r. So we have a cylindrical can. Okay, and the radius, they told us to use capital R, and the height is h. Now, we also want to express the area of the cans in terms of height and give a reasonable domain. So the other thing that I would do, if it's not specifically asked for, is I would write my constraint up here. So we were told in the problem that the volume of this can has to be 100 centimeters cubed. So 100 centimeters cubed must equal the volume of the cylinder, and the volume of a cylinder is the area of the base, which is pi r squared times its height. So we'll just leave that hanging for now. Now, if we want to talk about the area of the cylinder in terms of h, so let's just find the area first. So the area is the same thing as saying add up the surface area. So this is where the fact that this thing has a top and a bottom is very important. So the top and bottom of a cylinder are circles. So the area of a circle is pi r squared. There are two of them because they are the same size. So we have two of that. Then we deal with the side. So the side of a cylinder, if you imagine slicing this down the middle and then unfolding it, you actually get a rectangle, where the base of the rectangle is the circumference of the circle. So the circumference of a circle is 2 pi r, and then the height of that rectangle is the height of the can. So they want us to write this as a function of just h. So this means we need to eliminate variable r. So this is where your constraint equation will help with this. So what you want to do algebraically is you want to solve for the variable that you want to eliminate. So if we want to eliminate r, that means solve this for r, so that way when we plug it in down here, we have only h's. So solving this for r, I'm going to move everything that's not an r over to this side. So 100 divided by pi h equals r squared. And the square root of 100 divided by pi h equals r. And since the square root of 100 is 10, we can simplify it like so. So now I can come down and write my function, my area function, in terms of h. So a of h is 2 pi r squared. Well, I actually have an expression for r squared, so that's going to be times 100 over pi h plus 2 pi r, and we have r as 10 divided by the square root of pi h times h. So now let's clean this up a bit. So the pi's here are going to cancel. 2 times 100 is 200. So we have 200 over h. Over here, 2 times 10 is 20. Pi divided by the square root of pi leaves you with the square root of pi. And h divided by the square root of h leaves you with square root of h. So that simply leaves us with the square root of h times pi. So that's our function just in terms of h. It also says to give a reasonable domain. So you determine the domain not off of this equation, off the constraint equation. And the easiest place to find the domain is going to be when you've solved for one variable in terms of the other. So if we look at this relationship right here, remember domain means what values of h are going to be allowed to be plugged in down here. So the smallest h could be is close to 0. Now h cannot equal 0 because if h were to actually be 0, right, and we can see that up here, if h were to actually be 0, you would never get to 100 meters. So that means the low end of our domain is 0 not included. So it can get as close to 0 as it wants, but not included. Also, I think it goes without saying when we talk about the word reasonable domain, well, h is a height, so that the concept of even accepting any negative values just doesn't make sense here in the real world. You wouldn't have a negative height. You would just think of height as a positive number. Now, on the high end, the way that you figure the upper bound of h is, well, because r and h, if h gets big, r gets small, and vice versa. So then think about it in terms of, well, what's the smallest r could be? Because that would be the biggest h could be. So the smallest r could be, well, same issue. If we try 0, it can't be 0 or else you'd never get to 100, right? So r can get really close to 0 as well without being 0. So as h gets super, super duper close to 0, or sorry, as r gets super, super close to 0, right, as it gets smaller, h is going to get ridiculously big. So another way you can see if you've done practice on these have we call this an inverse proportion to each other. So when this is happening, we know that as this variable gets close to 0, this one's blowing up to infinity and vice versa. So the domain here is 0 to infinity. The types of problems, and if you look at some of the old finals, you'll see some optimization where this happens, where the domain is like real numbers. You'll notice that the constraint equation is set up in a way where you could actually legitimately plug 0 in and it turns out to give you a number. But in a situation like this where 0 is not possible, the most common domain in those situations are in fact 0 to infinity. So we've got our function, we've got our domain. And now they want us to find the value for h, which requires the minimal amount of metal. So we actually want to know what value of h is the absolute minimum. So we do that by taking the derivative, looking for critical values. So let's start with the derivative. So a prime of h, the derivative of 200 over h, that's the same thing as thinking as like 200 times h to the negative 1. So you would get negative 200 times h to the negative 2. So that would work out to be negative 200 over h squared. For the next piece, well, this is the same thing as saying 20 times all of this stuff raised to the 1/2. So the derivative would be 20 times 1/2, and then all of this stuff raised to the negative 1/2. So the negative 1/2 moves the radical down here. But then this is actually a chain rule derivative. So the derivative of the outside is here, but the derivative of pi h is just pi. Now we need to get a common denominator. But before I do that, I'm going to see if there's anything I can clean up first to make my algebra a little bit easier. So the negative 200 over h squared doesn't really clean up, but over here, 20 divided by 2 is 10. Pi divided by the square root of pi is just going to be the square root of pi. And then in the denominator, we have square root of h. So if I look at this, the common denominator is going to be h squared. So h to the 1/2, in order to get it all the way up to h squared, we would need to multiply it by h to the 3/2. right? Because you add exponents together. So 1/2 plus 3/2 is 4/2, which is in fact h squared. So then I also need to do this in the numerator. So the new function is negative 200 plus 10 times the square root of pi times h to the 3/2 all over, I'll make sure this is showing up on my camera here, all over h squared. So now we need to find our critical numbers. So as always, there are two types. So we need to verify, are there any places where the derivative does not exist? So if we look at this equation, the only problem area that I see is if h is 0, that would be a problem, but 0 is not in the domain, so it's not a critical value. Also, this is a h to the 3/2, so there's a square root implied, so that also means mathematically h can never be negative. But if we check in our domain, negative numbers aren't there. So there are no values that we need to worry about where the derivative would not exist. Now we need to determine, are there any values where the derivative would be 0? So we simply have to check the numerator for this, because only the numerator of a fraction can make it 0. So we've already eliminated any squirreliness in the denominator. So I'm going to set the numerator equal to 0. So that's going to give me 10 square root of pi times h to the 3/2 equals 200. And then I'm going to move everything that's not in h, right, by dividing to the other side. So when you divide 200 by 10, you get 20. And then the square root of pi is in the denominator. Now, in order to get h by itself, I need to raise each side to the 2/3, right? Because 3/2 times 2/3 would give us 1. So h raised to the 2/3 gives us h. 20 over square root of pi raised to the 2/3 gives us 20 to the 2/3 over pi. Now this cleans up a little bit, so 20 squared is 400. Pi or square root of pi squared is pi. So I've got 400 over pi all raised to the 1/3, or the cube root. Okay. So then what we need to do is we need to set up either you can do the first or second derivative test. It doesn't matter. My advice to students on this is you will always have the first derivative already there because you used it to find your critical values. So I always tell my students, take a look at the first derivative and then ask a question. Is the second derivative going to make it cleaner and neater to work with, or is it going to get worse? So most of the time in these problems, the answer is no. But if you have a polynomial, go for it. Second derivative, they just get better looking as you keep going. So this would be a quotient rule. This would get nasty. I just see no real benefit to even looking at the second derivative. So we'll just stick with the first derivative test. So I'm going to sketch the domain of the function, which is 0 to infinity. And I'm going to label this A prime because that is the test I'm running. So you do need to indicate on these problems for us what test you're running. So explicitly state you're doing the first derivative test. If you're doing a chart or a graph, make sure you label that as that derivative so that way we know what you're doing. Then I'm going to put my critical value. Okay. Now, remember, we want to work with exact numbers, but there are moments of these problems where that exact number might not give us any real comprehension of what we're doing. So your exact number needs to go here, but I don't know what 400 over pi cube root is. So if you approximate it in your calculator, that will help you to make sure you're choosing values correctly on your number line. So this is about 5. So when I pick values in this first area, I'm going to say let's let x be 1. And when I plug 1 in for h into this derivative, I get a negative number. And then I'm going to pick 10, just because it's something over here. It doesn't really matter which number you pick. And when I plug 10 into here, I'm going to see that this derivative is positive. So if I analyze this, remember the first derivative indicates increasing, decreasing behavior. So the function goes from decreasing to increasing. So this is indeed a relative min. So this is a relative or local minimum, all right? Now the question is asking for absolute minimum. So you have to make an argument when you're doing either the first or second derivative test of how do you know that this relative extrema is the same value you want for your absolute extrema. So when this happens, there's an important fact for any of you that took the flip class. Something we definitely showed you in the workbook. But if there is exactly one critical value on your domain, you can make the argument that that relative extrema must also be an absolute extrema. So since h equals the cube root of 400 is the only critical value on the domain of 0 to infinity, then it must be an absolute minimum. Okay, so then our final answer, because all we were asked to do was give the value of h, we can now confidently say this is the value of h. So in a typical optimization problem, once you've gotten to this step, once you've found the min, you've confirmed it's an absolute, I always tell my students there's a pause point right here, okay? And the pause point is go back and read the question and verify what they've asked for, because the critical value itself is very commonly not the answer. So this question was set up where that value of h was the answer, but they might have said give the dimensions of the can. So they might have wanted r and h. They might have asked for you to calculate something else. So that's why I tell my students there's always a little pause point here, because you may have to do more math with that value in order to report the actual thing you were being asked for.